Hey, what's up? Welcome back. Patrick here, and moving on to the next video dealing with domain range functions. So here we are given a bunch of equations of relations. We're going to have to state the domain and range from them, and then also whether the relations are functions or not. And before doing this video, I'm assuming that you have a background knowledge of how lines work, of how quadratics work in general. So knowing how to get x-intercepts or vertexes from different formats, I'm assuming you have a background knowledge of that because I'm going to be plotting these fairly quickly. I'll try to explain the characteristics as I go, but if you want more in-depth explanations of how these are working, you may have to go back and watch my previous videos on those specific types of graphs, right? Lines, quadratics, etc. So the first one, notice here, part A, we have just a regular line, y equals negative 4x plus 2. So let's make a quick sketch with these ones. Really, all you need is the y-intercept, the slope, and then you're good. You don't have to make a table of values or anything like that for these kinds of questions. So notice that the b value is 2, which is the y-intercept. So that's going to be here at 0 and 2. And then notice that the slope is negative 4, meaning that it's sloping downwards like that, right? If this was positive 4, it would be going up like that. And just a basic sketch like this is enough for this kind of question where we're just finding the domain range, stating whether it's a function or not. All right, so notice that the domain, well, this line extends infinitely, right? And so from negative infinity to positive infinity, basically all of the x values are going to get hit at some point, right, on this line. So we would say the domain, there is no limit or any restriction on the domain. It's just XER in interval notation from negative infinity to positive infinity. Okay, what about the range? Well, from the bottom to the top, notice that if we extend this infinitely, all of the y values are going to get touched on this line, right? And so there's not going to be any restrictions on the range either. So we would say it's just YER, and that's going from negative infinity to positive infinity, like that. For any line, unless it's a straight vertical line or straight horizontal line, the domain and range is always XER and YER respectively. Unless it's a word problem as well, then there could be restrictions. But for just a regular line, that's not just a horizontal line or a vertical line. So if it's in this y equals mx plus b format, domain and range is always XER, YER. There's never any restrictions. And then a line, it always passes the vertical line test. There's never multiple points that have the same x value. So this is indeed a function. And then moving on to part B, here we have a quadratic that's in vertex form. So we have y is equal to negative 3 bracket x plus 2 squared minus 5. Okay, so what is the vertex here of this quadratic? Because it's in vertex form, we can get the vertex right away. Notice it's going to be negative 2. Remember, it's always going to be the opposite sign here, and negative 5. And so remember, in previous videos, for the domain and range of a quadratic, what's the most important part? The location of the vertex and whether the quadratic opens up or down. And notice because the a value is negative 3, right? The a value is negative 3 here. That means this quadratic is going to be opening downwards. And so if you want to make a quick sketch of this, negative 2, negative 5, which is like over here, negative 2 and negative 5, and then this quadratic is opening downwards. And that's as rough of a sketch that you need. Okay, again, you don't have to go into details, making a table of values and stuff. We just need the vertex and then whether it's opening up or down. And then just from this diagram, it's going to be easy to see what's going to be the domain and range. Now remember, for a regular quadratic, as I've mentioned in videos before, there is no restriction on the domain, right? From negative infinity to positive infinity, these keep extending infinitely to the left and then infinitely to the right. So the domain would be XER in interval notation from negative infinity to positive infinity. But remember, for a quadratic, the range is restricted and it depends on the y value of the vertex and whether the quadratic is opening up or down. So over here, notice the y value of the vertex is at -5, and the quadratic is opening downwards, so there are no y values above -5 here, right, on this quadratic. So basically, it's all the y values below and equal to -5 that are being hit on this quadratic. So the range, all the y values such that y is less than or equal to -5, like that. Then in interval notation, remember, you always read from the smallest y values to the largest ones. And the smallest ones are going to start at -infinity because it's going to extend downwards, and they're going to end at -5, right? So for the range, you're reading from the lowest values up, right? So sometimes this messes up students with the interval notation, especially for the range. For the domain, it's kind of like, yeah, we're reading from left to right, but this quadratic is opening down, so your instinct is just to read from the top down, right? But when you are writing the range in terms of the interval notation, it always starts from the smallest y values, which are the lowest ones, and goes up to the highest y values, which are at the top. Okay, so the smallest y values are -infinity down here, and they're going all the way up to this y value of -5, and it's including the -5, so that's going to be a square bracket, like that. Okay, is this a function or not? Passes the vertical line test. All quadratics do. All regular quadratics, that is, sideways quadratics or sideways parabolas don't. But this is just a regular quadratic, so indeed it is a function. Now moving on to part C, here we have y equals the square root of x minus 4. Now, this one's going to be a little bit more intricate, a little bit more tricky. I'm going to talk about this pretending that you don't have any knowledge of transformations. In a future section in this chapter, we're going to be transforming the square root parent function. This is just going to be shifting it by 4 to the right. But let's pretend that we don't have any knowledge of that at this point when we're discussing the domain and range of a relation like this. Now, the domain, in general, here's what you want to write down. If you are square rooting any expression, right, any expression under the square root, that expression always has to be greater than or equal to 0. Right? You can't square root a negative value. You can square root 0, that's going to give you 0, and you can square root a positive value, but you can't square root a negative value. And so following this general rule here, that means that this expression, x minus 4, has to be greater than or equal to 0. And when is x minus 4 going to be greater than or equal to 0? Well, if we isolate for the x, bring the -4 over, that's going to happen when x is greater than or equal to 4. So in this particular relation, all the x values have to be greater than or equal to 4. Okay, if it's anything less than that, it's not going to work. So for example, if we plug in like 3, if we plug in 3 for x, 3 minus 4 is going to give us -1. We can't square root -1. So that's not going to work. And so the domain starts at an x value of 4. It's all the real numbers starting at 4. So it's XCR, x is greater than or equal to 4. That's going to be the domain right there. And then for the range is a little bit trickier to think of. Let's do it in a different color here so you know I'm talking about the range the whole time. What you could do is actually for this, make a table of values starting at the x value where it was restricted. So you would start at 4. And so notice if I plug in 4 for x, 4 minus 4 is 0, square root of 0 is 0. And then we go up. So let's go to the next x value of 5. 5 minus 4 is 1. Square root of 1 is 1. And then let's actually pick x values. Like, I know we could use 5.1, 5.2, and all of the numbers after 5, right? But then we're going to get decimals here. So let's just pick x values where we're going to get a rootable number. So the next one would be what? 4. You want to get 4 under the square root, so that's going to be at an x value of 8. So 8 minus 4, square root of 4 is 2. Next one, you would want to get 9, right? So that would be what? 13? 13 minus 4 is 9. Square root of 9 is 3. Okay, and I know, again, that there's x values in between 4 and 5, between 5 and 8, right? It's just that the y values in the table are going to be decimals, so I'm just trying to keep the table with just integers. But you can plug in other x values as long as they are greater than or equal to 4 in the table. And so what you'll notice is that the y values, they're starting at 0 and then they're going up. And basically, the way that this is going to look, this relation, and we're going to get into more detail on how a graph like this looks like when we're talking about transformations, is that we're going to start at this coordinate 4 and 0, which is going to be here, and it's basically going to curve up like that. Okay, so as we mentioned already, for the domain, x is greater than or equal to 4. You could see that, right? It's starting at 4, and it's all the x values all the way to infinity. I actually forgot to put the interval notation here. So for the interval notation, we're starting at 4, put a square bracket there, and it's going towards infinity, right? Left to right. The leftmost point is at an x value of 4, and then the right, this keeps going on forever, so the x values are going to end at infinity. Now what about the y values? Remember, the y values, we look from the bottom to the top. We read from the bottom to the top. So notice that the lowest y values are going to be 0. And then it's going to be all the y values above that, right? As we go up this function. So we would say the range is YER, y has to be greater than or equal to 0, like that. Okay, and then in interval notation, the bottommost value is 0, including the 0, and then it's going to go towards infinity, right? From 0, from a y value 0, all the way to infinity on this graph here. And then is this relation a function? Yes, it passes the vertical line test. There's not going to be any point on this relation, any scenario on this relation where there's going to be multiple points for the same x value. So yes, this indeed is going to be a function. So if you get something like this, if you don't want to use transformations and stuff like that, or you don't remember how to use them, you got to remember this here. So first you would get the domain with this property, right? Anything you're square rooting, that expression always has to be greater than or equal to 0. Find out the x values when that's going to happen. And then from there you can make a table of values and then draw a rough sketch to get the range. Quick little intermission here. Wanted to mention a few things quickly and we'll get right back into the question. First off, if you are getting value from this video, if you can please like the video and subscribe to my channel, it does help me out a lot. Number 2, if you're watching this on YouTube, you can go to the description box and there is a link that will take you to my website, allthingsmathematics.com, where all my courses are organized so you can watch the videos in order. For lots of the courses, at the end of the chapters, you can find tests that you can practice with, and the tests have video solutions as well. Number 3, if you feel like you need personalized help in tutoring, give me a shout. I currently tutor students 7 days a week over Zoom, both high school and university students, one-on-one and in groups. You can text me. My contact details are on my website. And lastly, feel free to forward the website to any of your friends who are also taking the course, who you feel can benefit from these videos as well. Hit me up on all my socials. It's All Things Mathematics for all of them. Back to the video we go. Moving on to part D, we have another quadratic. This time it's in a different format. Notice here it's in standard form, negative 2x squared plus 12x, right? Before we had it in vertex form. So actually this one is tougher to deal with. What's nice about the vertex form is we could get the vertex right away, and that's what affects the range for a quadratic. Here, the vertex is not directly given to us. And so if you remember, there's multiple ways to get the vertex. We could find the x-intercepts, and then the vertex, the x value, or the axis of symmetry is going to be the midpoint between those x-intercepts. So if we were to do that, this is actually going to factor pretty smoothly. We could take out a negative 2x, and we'd be left with what? X minus 6. And so from here, this x value by itself, we could tell one of the x-intercepts is 0. And then over here, the other x-intercept is 6. Okay, so if we draw a rough graph of this, we have an x-intercept of 0. We have an x-intercept of 6. Now, the a value is negative, right? This negative 2, meaning that this quadratic is opening downwards. And so if we draw a quadratic like that. Now, this was at 0, the x-intercept. This was at 6. So where is the x value of the vertex going to be? Well, it's going to be the midpoint between the intercepts. So you could add the intercepts divided by 2 to find that axis of symmetry. 0 plus 6 is 6, divided by 2 is 3. So we know the x value of this vertex is going to be 3. But remember, that's not what's important. We need the y value of the vertex. That's really what's going to be affecting the range of a quadratic. So if we plug in 3 here, we'll have what? 3 squared, 9, negative 18, plus 36. That would give us positive 18, like that. And so now, at this point, we have enough information to find the domain and range of this quadratic. Now, if you wanted to get the vertex, you could also complete the square. Again, I'm not going to go into details on how to do that. You could go back to grade 10. I have a bunch of videos on this process, but if you were to complete the square, you take the negative 6 divided by 2, square it, that'd be 9. So we'd have negative 2, x squared minus 6x plus 9 minus 9. Just want to show you how we would get the same vertex. Take the negative 9 out. We have to multiply it by what's in front, the negative 2. Negative 2, x squared minus 6x plus 9 plus 18. This is always going to be a perfect square trinomial. X minus 3 squared plus 18. So notice we get that same vertex of 3 and 18 from the vertex form if we were to take this and convert it to vertex form, right? And this negative 2 means it's opening downwards. And so from here, we can find the domain and range from this graph. So remember, the domain for a quadratic is always x, e, r, right? There's no restrictions on the x values from negative infinity to positive infinity. In interval notation, it would be from negative infinity to positive infinity, like that. Now the range, again, as we mentioned many times, depends on the y value of the vertex and whether it's opening up or down. So notice the y value is 18 and this parabola is opening down, meaning that the maximum y value is 18. So it's basically all of the y values that are less than or equal to 18. So y can be any real number as long as it's less than or equal to positive 18. In interval notation, we would say the y values go from negative infinity. It's all the y values from negative infinity to positive 18, and it's including the 18. So we would put a square bracket there. And then a parabola is always a function. It is always passing the vertical line test. And finally, moving on to part E, this one's going to be a tricky one. We got the square root of x squared minus 4, and then actually as a bonus, I also included the square root of 4 minus x squared. Okay, because the process for solving both of them, getting the domain and range, is going to be similar, but they're going to be totally different relations, as you'll see at the end. But process is similar, so thought I would include it because it's kind of like killing two birds with one stone, and you could see how both of these are going to relate. But in both of them, notice that we're taking the square root of an expression. And a few relations back, I said whenever you see that, that basically means that the expression has to be greater than or equal to 0, because you can't square root a negative. However, isolating for x in this one is going to be a little bit tougher because it's a quadratic. Okay, before it was a linear function, we were just able to isolate the x directly. There was a linear there was just a line here under the square root. But in this case, it's a quadratic. And just in general, if you want to write this rule down, whenever you're trying to look for when a quadratic is greater than or equal to 0, you're basically trying to find when is it going to be above the x-axis. Or basically, when are the y values going to be greater than 0? And then we're also, because it's greater than or equal to 0, we're also trying to find out when does it hit the x-axis, right? When are the y values going to be equal to 0? And that's going to be at the x-intercepts. So we're trying to find the intercepts and then also when it's above, right? So if we just draw like a random quadratic like this, we're trying to find this interval and this interval. That's what it means when a quadratic is greater than or equal to 0, and then also when it equals 0, meaning the intercepts right there. And so knowing that, trying to find out when is this quadratic going to be greater than or equal to 0, notice that x squared minus 4, that actually factors smoothly into x minus 2, x plus 2 as a difference of squares. And we want to find out, right, in the process what the x-intercepts are going to be. So sometimes you'd have to use the quadratic formula if it doesn't factor smoothly. In this case, it does factor smoothly. So if we draw this quadratic, now as a heads up, when I'm drawing this quadratic, this drawing here, this graph, is only x squared minus 4. It's not the square root of x squared minus 4. So I want you to kind of temporarily forget about the relation that we were given and just pretend that this video is about this for now. Right? So when I'm making this drawing, I'm just focusing on this inequality right here. I'm trying to find out when is x squared minus 4 going to be greater than or equal to 0. And so the two intercepts are -2 and +2, meaning that the axis of symmetry is going to be 0. Not that that is important. All that's important is where the intercepts are, and then when is the quadratic going to be greater than or equal to 0. And so if you look closely, where it's going to be greater than or equal to 0, well, it's going to equal 0 at 2 and -2. Those are the intercepts. That's where the y value is going to be 0. And then when is it going to be greater than 0? Well, it's going to be greater than 0 here on this portion and then on this portion. And that keeps going, extending infinitely. Right? And so we could say that this quadratic is going to be greater than or equal to 0 on two intervals when x is less than or equal to -2, or when x is greater than or equal to +2. Okay, those are the two intervals where this quadratic is going to be greater than or equal to 0. You could also show this here on a number line as well, right? So it's basically, if this is like 0 on the number line, it's basically all the x values greater than 2 and all the x values less than or equal to 2 right here. Okay, so any x values in between are not going to work on this relation, because if you pick any x values in between, like if you pick 0, for example, if you plug in 0 for x, you would get -4 under the square root, can't square root a negative. If you pick like -1, right? If I plug in -1 here, -1 squared is +1 minus 4 is -3, can't square root a negative. If I pick +1, right, 1 squared minus 4 is also -3, can't square root a negative. So any values, any x values here are not going to work on this relation, and so they're not part of the domain. And so what we would say here is basically the domain for this relation is it could be any x values, x can be anything, as long as it's greater than or equal to, or actually let's say first, less than or equal to -2, or greater than or equal to +2. In interval notation, right, we would say it's from -∞ to -2, including the -2, so we would put a square bracket there, or, right, this is like the union symbol, or it could be from +2 to +∞. That would be that interval right there. Okay, so this is how you would state the domain in both the set notation and in interval notation for this particular relation, right? So when you're trying to find out when a quadratic is greater than or equal to 0 or less than or equal to 0, it's a little bit more tricky. You got to graph the quadratic, you got to get the intercepts, and then see, okay, when is the quadratic going to be above the x-axis. Now to find the range, I'm actually going to make a table of values like we did in that other relation when we were dealing with a square root. But notice here, we're actually going to make two tables of values because there are two intervals to work with, right? So I'm going to make a table of values for all the x values less than or equal to -2. So let's say like -2, -3, -4, -5. And over here, all the x values greater than or equal to 2. So 2, 3, 4, and 5. And so what you just want to see is what's the behavior of the y values going to be, right, as we extend out in these domains. So if I plug in -2 and +2, I would get 0, right? The square root of 0 is 0. If I plug in -3 squared is 9, -4 is 5. So we would have the square root of 5. I'll just leave it as an exact value. Okay, -4 squared minus 4 would give us 12, and then 25 minus 4, so root 21. And actually the same thing's going to be happening here. It's going to be a symmetrical function, right? Because -3 squared and +3 squared, both of those would give you 9, which would give you that root 5 as a y value. And so notice that the y values, basically what's happening is that they are starting at 0, and then they are increasing, right, as we extend out into the domains. So the way that this relation is going to look like is, okay, at 2, and then at -2, right, it's going to equal 0, and then the y values just become positive, like this, right, and it's symmetrical. And so that's how it's looking. So if you took this relation and graphed it in Desmos, you would get something like that, right? And so from here now we could tell, okay, what's the range going to be? What's the behavior of the y values? Well, they're starting at 0, right, at both of these points, and then they are increasing after that infinitely to positive infinity, right? Because these are going to keep increasing forever, right? They increase at a slower and slower rate because they are concave down, right? They're kind of curved this way. They're not increasing like an exponential function. But nevertheless, they are going to keep increasing forever and ever, right? And so basically, what the range is going to be is basically all of the y values that are greater than or equal to 0. Or we could say from, in interval notation, from 0 to infinity, right? From 0, these 2 points, to positive infinity on both of these. All right, so a bit more of a complex relation, but same process. You're trying to find out when is that expression under the square root, that x squared minus 4, when is it going to be greater than or equal to 0? Found out the domain, and then make a table of values so you could see what's the behavior of the y values. And so you end up with a diagram like this, and you get your range. And then finally, as I promised, this last relation, y equals the square root of 4 minus x squared. So same process, trying to find out when is this quadratic going to be greater than or equal to 0. But notice that this quadratic, 4 minus x squared, it's a lot different than this quadratic. This quadratic here, it's actually going to be opening down, right? If I rearrange this, I got like -x squared plus 4. We have to find out when is that going to be greater than or equal to 0. Well, what we want to do is get the intercepts for it. So same thing, I could factor out a negative, and I'd have x squared minus 4. And then that factors as a difference of squares. So actually the intercepts of this quadratic, they're going to be the same. Okay, it's going to be a -2 and +2 from these factors here, but the a value is -1, so this quadratic is actually opening downwards like that. All right, axis of symmetry is still at 0. Vertex would be here at 0 and 4, versus the other one, it was opening upwards, and the vertex was at 0 and -4. Okay, but this one is opening downwards right here. And so remember, we're trying to find out when when is a quadratic greater than or equal to 0, when is it on the x-axis, the intercepts, which is at -2 and +2, and then when is it above the x-axis, when are the y values positive? And notice that that's on this interval right here, right? And so in this particular case, what the domain is going to be is it's going to be, x can be anything as long as it's in between and equal to -2 and +2, like that, right? That is when this relation is going to be positive. Then you could test it, right? So let's try to plug in -3. If I try to plug in -3 here, I'll get -3 squared, which is 9. 4 minus 9 is -5, and we can't square root a negative. Or if I try to plug in like +4, right? Something outside of this domain. So if I try to plug in +4, 4 squared is 16. 4 minus 16 is -12. Can't square root a negative, right? And so in this case, the domain is a lot different because that expression under the square root is different. It almost looks the same, but it's not because it's actually a quadratic that's opening down, and so it's only on this interval here when it's going to be greater than or equal to 0, not on that outside interval. And so for the range, what we could do, as usual, let's make a table of values. Now we only have to make one table of values because there's only one interval, right, that we are working with. So let's start at -2, and then let's just do -1, 0, +1, and then we end at +2. So if we plug these in, -2, if we plug it in here, 4 minus 4 is 0. If I plug in -1, 4 minus 1, -1 squared is 1, 4 minus 1 is 3, so we get square root of 3. If I plug in 0, 4 minus 0 is 4, square root of 4 is 2, and then it's going to be symmetric like that. And so if we graph these, right, so what's going to happen here, -2, +2, I got 0 and 2, that's going to be up here, and then like -1 and √3, it's going to be somewhere here, +1, √3. It's basically looking like that, right? So it should be a little bit more curved, but if you took this, graphed it in decimals, this is how it would look like. And so there's no domain outside of the -2 and the +2, right? It's only in between these. And so from here, well, what's the range going to be? Well, the range starts at 0, that's the lowest y value, and then it keeps going up and up and up until this y value of 2. That's the maximum y value, and then it comes back down. And so basically the range is all of the y values that are greater than or equal to 0 but less than or equal to +2, like that. We could see that from the graph. And actually we didn't give the interval notation for these, I just realized. So the interval notation for the domain, we would say from -2 to +2, right? It's including those, so there's square brackets here. And then for the range, we would say from 0 to 2, like that. And then checking whether this is a function or not, notice that it is going to pass the vertical line test, right? There's no pairs of points that have the same x value, so this is going to be a function. And I'm actually realizing that I didn't state whether the previous one was a function or not, right? The square root of x squared minus 4. So let's bring back that diagram quickly. So remember, it was at 2 going like this and -2 going like this. But that other one is a function as well because it's also passing the vertical line test everywhere, right? So that one was a function as well. That was the y equals the x squared minus 4. Now when I was talking about whether this one was a function or not, I just realized I didn't talk about that in the other one. All right, so both of them are functions indeed, but notice that the domain and the range is totally different. Even how they look is totally different as well, but the process is similar, right? So again, anything with a square root, that expression, trying to find out when is it greater than or equal to 0. That's how you get the domain. And then for the range, I would just take those intervals that you got and then make a table and then plot it. And then you can sort of figure out visually and from the table what the range is going to be. And that is the end of the video. Hopefully you enjoyed that. If you want to find more videos like this, you can go to my website, allthingsmathematics.com. Over there, all my courses are organized for both high school and university. All the videos are organized by chapter. Also, if you have any questions, you can hit me up. My contact details are also on the website. Enjoy your day, and I'll catch you in the next one. Peace out.